Aldol reaction. Aldol. One of the top 10 reactions in organic chemistry. There's about 20 or 25 top 10 reactions. Intramolecular aldol reactions. Do we get a four-membered ring here that's possible, theoretically possible? What does your four-membered ring look like? That is, instead of this 1, 2, 3, 4, 5, 6, what if this enolate attacked here? Electrons up. What would that look like? Well, it'd be a four-membered ring because we have 1, 2, 3, 4 carbons here. Let's make this bond electrons up, so this moves to the oxygen. This carbon attacked that carbon, electrons on the oxygen. This carbon was next to a carbonyl. That doesn't seem right. Hold on. It was not, that's not where it was. Because between the two carbons, we have 1, 2, 3, 3 carbons, 1, 2, 3, next to carbonyl. Carbonyl is actually here. We're going to make the ring here. This carbonyl is not part of the ring. We're making a ring right here. 1, 2, 3, 4. Okay, coming off the original carbonyl. Carbon is a methyl. Basically, I'll do that again, yeah. Used to be anion here, and this used to be carbonyl. Ugly bond angle. But these electrons bonded here, and these electrons moved on to oxygen. So that's how the bond ended up here. And electrons moved on to oxygen. That became minus here. From there, what do? We pick up proton, yeah? And what do we do next?
Couldn't that polymerize?
This structure here?
Without, if it didn't pick up a proton, the electrons on the oxygen attack another carbonyl.
Yeah, but that's not going to lead anything. It's just going to get kicked right back off.
Okay.
If you look at the aldol reaction, we then eliminate water to make the double bond here. Ultimately, it's going to lose H2O. And ultimately, the four-membered ring we're going to get is going to look like that there. How do we do? Is that what you got? Everybody good? But this is not the product of the reaction because the six-membered ring is going to be favored. Yeah? One below. What size ring are we making down here? What size ring did you get down here? 5-membered ring? Either end's the same. If we had anion here, this would attack here. That'd be a 1, 2, 3, 4, 5, 6, 7. That's not as good as 5 because if we had anion here, and this attacks here, electrons up. It would be a 5-membered ring, and what will it look like? It's going to have a ketone coming off. That there. Is that it? Basically, if you go backwards, the aldol gives the alkene. It makes the alkene alpha beta unsaturated to a carbonyl or some other similar functional group that's electron withdrawing. If we break this apart, we can go backwards to one of these was an enolate carbon. Which one was it? Left or right? Right, the one next to the carbonyl. The other carbon was originally what? Carbonyl, right. Carbonyl. Boop, boop, boop. Boop. Enolate carbon, carbonyl. And that's the starting material. We just went back to the starting material, right? This anion condenses onto that carbonyl. It reacts, and ultimately we lose water to make the alkene. You know the mechanism. How could these be made using an aldol? First one. Someone name the two starting materials that would be used to make that by an aldol reaction. Yep, acetophenone. And propanol, and you would treat this with some type of base. Most often it's some type of hydroxide base as a catalyst, KOH, sodium hydroxide. And that would be a mixed aldol. Hopefully this would not self-react. Two different places to form enolate. Sometimes you may have selectivity, sometimes you may not. But ultimately, this is the two that would give this by an aldol. How about the second one? Can you name the two starting materials? And that's a trick question. It's only one starting material. What's the name of the starting material?
Cyclohexanone.
Cyclohexanone, yes. This is where it's reacting with itself, two equivalents. Hydroxide is most common. There could be a variety of other bases. You could even use triethylamine for caps. In some cases, triethylamine may work at a sp3 amine. Not an anion, it's less basic than hydroxide. Sometimes sp3 amines are basic enough to do aldols. About the third one.
Isopropanol or isopropanol. AL.
Somebody got something? Look good? This particular compound here is an example of, with an activated methylene. I don't know if I said activated methylene before, we said methylene, but activated methylene, very common between the two electron withdrawing groups. This happens to be a cyano group, the other is carbonyl. It's going to be very easy to make anion here, and then this will condense onto the carbonyl. Same aldol mechanism, elimination of water to make the alpha beta unsaturated carbonyl. It's also alpha beta unsaturated to the cyano group. If you did an aldol reaction during the 8-week lab, it involved reacting the fluorinone, the oxidation product that had the carbonyl, the ketone, and it was reacted with a compound like this that had 2 nitriles. Anybody do that aldol reaction? 1 or 2 people maybe did it. Yep. It's okay to admit to it. I know at least one person did it. It was bright orange product, unless I'm dreaming. Okay. Use this and the fluorinone, the 2-nitrofluorinone, and then aldol. There's no carbonyl here. These withdrawing groups can be other things like nitriles or sulfone groups. Carbonyl is most common. This one had 1 cyano group, 2, that's called melanonitrile. If this was diacid here, it would be malonic acid. We saw that earlier with the malonic ester synthesis. Relatively acidic here. Okay. There's another example of an intramolecular. We're going backwards. Okay, you can try that one. Synthesis of Vioxx. Let's see that one again. The white handout. There's chemistry here to make a $1 billion drug, and unfortunately that drug no longer is used, and a lot of sad people who were making a lot of money. But they're making lots of money on other drugs now. There you go. What is that? About 16 carbons, about 4 oxygens, a sulfur. Put them together, $1 billion drug.
Probably more involved than that.
Go ahead.
Might be more involved than that.
What?
But there are like 5 rules it has to follow.
5 rules?
Yeah.
Here we go. We got some chemistry we know, like Friedel-Crafts, alpha halogenation, SN2. The last step here is an aldol condensation. What's going on here? What's attacking what? Triethylamine is used as a base here. Somebody identify the enolate carbon. What carbon is a nucleophile here? Carbanion. What's attacking what?
The aromatic.
The one that's, yeah, between the carbonyl and the aromatic ring, but that's not on the side of the
Yes, I believe this anion is attacking what?
The carbonyl.
1, 2, 3, 4, 5. It's attacking here. There's an oxygen in the ring. 5-membered ring. There's an oxygen in the ring. You can also break this apart. The alkenes being formed in the aldol. Which carbon, top or bottom, was originally enolate?
Top.
Top. How do you know?
Because you can know where the carbonyl left.
Oh, it's the one next to a carbonyl, because that's where enolates are. They're next to carbonyls, or cyano groups, or something else. Okay? The top was enolate, and then we come over here, and this bottom carbon was originally what?
Our anion.
Carbonyl. The other carbon is originally carbonyl, and then that's the ring with the sulfur. What's the name of this functional group here? Sulfone. If it was just sulfur, it'd be a sulfide or a thioether. One oxygen is called a sulfoxide. 2 oxygens is called a sulfone. You do not need to know those two. If there was a nitrogen bonded to the sulfone, it would be called a what? Like an amide, it would be a sulfonamide. Sulfonamide is how it's pronounced, right? You know sulfonamide, that was on the organic 1 functional group list, at least for my class. And if we open this back up, what do we have? And if we make that neutral, what do we have? We got the starting material. So an intramolecular aldol condensation finished it up and gave the final compound. Is there another possible aldol that could have occurred here instead of what did occur? No, not really. I mean, if you made anion here and attacked here, well, that's not an aldehyde or ketone. You only condense onto an aldehyde or ketone. That would also be a very strange 3-membered ring transition state. But that's not an aldehyde or ketone over there. That's an ester over there. You're going to kick off that oxygen. Not the carbonyl oxygen. An aldol reaction involves an enolate reacting with an aldehyde or ketone. If you attack an acid derivative, you're going to do an additional elimination chemistry, and you're not going to get dehydration and loss of the carbonyl oxygen. It's an aldehyde ketone reaction. Enolate attacking an aldehyde or ketone and eventually losing water. Okay. The Klein textbook shows a biochemical application, if you've seen it, cross-linking of collagen by an aldol reaction makes the meat from older animals tougher. Older animals typically have tougher meat. The opposite of that would be something like veal. Isn't that like very young?
Baby cows.
Uh-huh. Very tender. Why does the meat get tougher as it ages? Cross-linking of collagen by an aldol reaction. Nice application in your textbook, Klein textbook. Using the Klein textbook. Okay, B. Not sure what A was, but I'm sure you can find what A was if you look back. It might have been the aldol reaction. B. Claisen condensation. Okay, esters. Aldol is aldehydes and ketones. What type of chemistry can we do with esters? And from enolates. Can an enolate attack an ester? Why, yes it can. If you take this ester, in this case two equivalents, treat it with a base first. What can this base do?
It takes
Well, it can act as a nucleophile attack carbonyl, but that's not going to give anything because you kick that off with that, it's just the same thing. But we can make some enolate over here. We can look to do chemistry over there. What can it attack?
itself.
It can attack another molecule, the carbonyl of another molecule. It's just a nucleophile. And if this nucleophile comes in here and attacks electrons up, we're just going to get electrons up. It's just a nucleophile adding to carbonyl to make this bond. But what nucleophile added? Well, it was that. It's pretty big. You got to keep track of it. It's going to look like there's the first carbon, and then we got two others. Does everybody agree that's the nucleophile adding to the other carbonyl? Nucleophile is just the enolate. This is the same first step as the aldol. The difference is this original carbonyl has a leaving group. With the aldol, I did not have anything. We had to protonate. We eventually lose this. But here we take an acid derivative, and the carbonyl can reform and kick off the leaving group. We're doing acid derivative chemistry here. Leaving group. Carbonyl reformed. And when it reforms, what do you get? What do you get?
Product plus methoxide.
So we get that. Carbonyl reformed here.
Wait.
What is that? What is that? Okay, I was hoping you'd say it's product. It's product, right? It is a beta-keto ester, yes. Is that product?
Yes. Yeah.
It is product. But this is not the end of the reaction.
Work up.
Because what else do we produce here?
Methoxide.
Methoxide. We started with methoxide, but I didn't show the acid-base reaction. It took that, we made this plus what? Plus methanol. Took the H. But here we reformed methoxide. So what do you want to call methoxide in this reaction? You might want to call it a catalyst. It's actually not catalyst here, because it's not actually reformed, because the reaction's not over. At this point, this is going to take an H. Look at this H here. Does it have any acidity?
Yes.
What's the pKa of this H approximately?
20.
Over here, the pKa was about 25. Now, this CH sits between two carbonyls. This has a pKa of about 12. I may have said a little bit something different last time, but close. 11 to 13, 12, it's somewhere here. And this is acidic enough that this is going to take this H I'll just call all that R. And this is the end of the reaction. Because we're making something that has got some acidity. And at this point, do you have any methoxide left? No. Methoxide is not a catalyst here. It's not reformed. I mean, it is here, but at the end of the reaction, it's not there. So it ain't a catalyst if it ain't there at the end. Question?
Wouldn't it make an alcohol in the end?
Yeah, here's the alcohol.
I mean, couldn't that charge go pick up electrons on the aldehyde and then after an H plus workup it'll make an alcohol because you have more substituted?
No,
alkene?
what do you mean aldehyde?
No.
Kicking the electrons up is resonance. The electrons are kicked up, yes.
Well, wouldn't you want to make a more substituted alkene
What do you mean?
between the aldehyde and that
There's no aldehyde in this compound.
carbonyl? And
What do you mean more substituted alkene? There's no alkene here.
couldn't you make one though?
How?
Those lone pairs attacking the carbonyl, kicking the electrons up, and then
That's resonance.
Yes, sir. And then
That's happening right now.
okay.
In fact, that's the major resonance structure.
And after
What's
H
the
plus-
major resonance structure of what I have drawn there?
The blend.
It's some resonance structure with the charge on oxygen.
But after H plus workup, wouldn't it protonate it?
They make an enol and then
If you protonated that, you would have an enol.
Okay.
And what do enols do? They tautomerize. Which is going to be favored at equilibrium, the enol or the keto form? Keto. Okay. So that's a major resonance structure, and it's an enol, but everything comes back to carbonyl. That's it.
Okay.
Methanol. There's no methoxide here at the end. Methoxide is not a catalyst. You actually need a full equivalent. Because we just did one reaction. One molecule was converted to this. If all you want to do is convert one molecule, well, all you need is one molecule of base. But you're not going to be able to see that molecule. If you want to be able to make anything that you can see, for every molecule you make, you need one of these. So it's stoichiometric. You need a full amount. Okay? You need a full one equivalent. It's not catalyst because it's not regenerated at the end. It's not present at the end. It was consumed because what you made was acidic. Basically, your product consumes the base, and so you need more base over there. What's the purpose of the H plus workup in my reaction?
To satisfy
back on.
that.
Well, if you got to put the proton on. Because that's how it is at the end. And then if you want to work it up, you got to supply some acid. Because methanol is not acidic enough to protonate it. If it was, you would go back to here. But this is an equilibrium. That's 12. What's methanol? It's about 16 like water, which is favored, 12 or 16.
16.
16. So the equilibrium is like that. Can you see the other arrow? Basically, a difference of 4 is enough to be pretty much complete. You need to supply a proton here. Question?
Why is it 2 equivalent of methanol at the end?
Why is it 2 equivalent?
Yeah. Where's the other one coming from?
The very beginning.
You actually make one methanol. Right?
The very beginning when you.
Hold on. 2 equivalent of methanol?
You start with one, then you would make one, right?
Where you start with the methoxide and you make the methanol from there. That's why you wrote it. at the
Yeah, in the
beginning.
first step. Methanol created.
One starts as the base and the other is the leading group.
What's the question again? Why is it two equivalent?
Yes.
Why is two equivalents formed? I think the problem comes from calling this one equivalent here. It's at least one equivalent. It's one equivalent plus catalyst, if that's right. It's or do you actually need two equivalents? One equivalent to take the original proton.
And then, well, it's one equivalent because one leaves the leading group.
Yeah, but you also generate a methoxide right here.
And that's what takes the other one. That's two.
It's one equivalent because one methanol came from this. The other methanol came from the leaving group being protonated. Because originally you have a methoxide here and here. That's methoxide. This gets kicked off as methoxide. So this was the leaving group here. Yeah, okay. One equivalent. I'd have to really look down at it, look at it closer. One equivalent plus. I think it's just one equivalent. Yeah. The other methoxide came from the leaving group. If I'm missing something here, ask again. This is called a Claisen condensation. We're actually not forming water. Condensation often refers to forming water. What did we form here? There's sort of a low boiling liquid that may have come out.
Methanol.
We form methanol. Got methanol over there. We actually form two equivalents of methanol. One coming from here, the other coming from the leaving group. And the methanol, if this is done at a certain temperature, can kind of come out, boil out, and condense out. So it's an enolate attacking an acid derivative, and the esters are most common here to be attacked. And we don't get an alpha-beta unsaturated carbonyl. Claisen condensation, Claisen reaction gives what?
Beta ketone
A
ester.
beta ketoester. And here it's an enolate carbon that attacked an acid derivative. But the carbonyl was reformed here. Where an aldol, you would have ended up losing this oxygen, you would have made a double bond here, an alkene. Acid derivatives don't have other leaving groups other than the carbonyl oxygen. So this is called a Claisen condensation. It's really a dimerization here because we use two equivalents of the same ester. Our product is acidic enough that it's going to consume the base. Because of that, the base is not a catalyst. You need a full equivalent here to do this reaction. With the aldol, the base is a catalyst. You can do mixed Claisens, like mixed aldols. Please look at those. I want to jump ahead to number 3. introduce this. Michael additions. You may have heard of Michael Jackson. You may have heard of George Michael. Neither one of them dealt with the Michael reaction, but just letting you know that they're not involved. Michael reaction. What can we do with alpha, beta, and saturated carbonyls? We can add nucleophiles to them. Here's one here, alpha, beta, and saturated ketone. Now, for many moons now, we have added nucleophiles to carbonyls. Nucleophile add to carbonyl, electrons up. We would get this anion, right? That's called a direct addition to a carbonyl. Direct addition. It's also called a 1,2 addition. Because the nucleophile is adding here, and the electrons end up on the next atom. So 1,2. We will compare that. That may make more sense when we look at 1,4. Okay? So that's also called a 1,2 addition. And again, we've been doing that for a month now. All right? We can protonate that oxygen, maybe you get an alcohol after the nucleophile adds. Maybe a fun workup. With this type of compound, though, alpha, beta, unsaturated carbonyl or analogous functional group, we can also do nucleophilic addition here to the beta carbon. The nucleophile, often an anion, I'll show this as an anion, can add here, and electrons move here. And doesn't this give this? Yeah? Now, what type of product is this? Anion, but what do you call that type of anion? It's an enolate. It's an enolate anion in this form. Now we can supply an H plus source and put the H on, and we can get a product like this. Ultimately, the nucleophile will add to the beta carbon. This has resonance structure. Let's go back to the enolate. Resonance structure, right? Electrons here, electrons up. Is that resonance? Resonance, yeah. I mean, we've been showing enolates like this, but isn't this actually the major resonance structure?
Yes.
Right? Negative on carbon or oxygen, which is better?
Oxygen.
This is actually the major resonance structure of enolates. But we typically would just show it like that because we react on carbon. This is where earlier you said move electrons up. I said they're already up there. The structure's already, this is just resonance. You got to know, yes.
If you had a longer chain with the nucleophile, could those electrons in the oxygen form a ring and kick off the nucleophile again?
Depends on what this was. If it was longer, though, we're not going to be adding the nucleophile. We're going to have to look at that. Why are we able to add nucleophile here?
Because you had an acidic H.
What does it lead to?
You know,
It leads to an enolate, which is stabilized enough to do this. Okay? This terminology. Why is it called a 1,4 addition? Because if nucleophile adds here, let's call that 1, where do the electrons end up at? Remember, they're predominantly on the oxygen. That's major. And that is what compared to 1?
4.
4. 1, 2, 3, 4. They added here, nucleophile added there, but the electrons ended up on the oxygen 4 away. Called a 1,4 addition versus here, nucleophile added here 1, 2. This is also called a conjugate addition. Doesn't say it here, conjugate. Because the resulting anion is conjugated with the carbonyl. Or you could say the alkene is conjugated with the carbonyl. Because of the alkene conjugation, that's why we're able to do this. Because typically we do not add nucleophiles to alkenes. I thought this was here. If we just have an alkene like this, you do not add nucleophiles to alkenes. We never have done that. Alkenes are not polarized enough. There's no dipoles. Now, if this was oxygen, I thought this was here. Is this on the next page? What I'm showing here? No? No? We've done this plenty, right?
Yes.
That's because this is polarized. This is a polar carbonyl. This carbon's partial plus. It's more electrophilic. We've never added nucleophiles to alkenes. But because the double bond is conjugated with the carbonyl, we can. That's why it's often called a conjugate addition. Typically, alkenes are nucleophiles themselves, so they attack electrophiles. Like an alkene attacking bromine or MCPBA to make an epoxide. The alkene is the electrons attack something. Okay? All right? We can do this with these alpha beta, and they actually tend to be pretty electrophilic, pretty reactive. There's one other time where we've added nucleophile to alkene. It wasn't an alkene, but it was analogous. It's got to be in here. Where am I? We got to skip over here. Turn over here. When we do NAS, we are adding nucleophile to a carbon-carbon pi bond as part of the aromatic. What was the requirement for NAS?
Had a strong bond with the pro or
Strong electron drawing group ortho repair. Why? What did that allow us to do?
resonance into the
That we
carbonyl.
get the charge onto
The resulting charge landed on a heteroatom. And that made us able to do NAS. When we do a Michael reaction, where does the resulting charge land? On a heteroatom. Oh, that's the minor resonance structure. Let's look at the major one. Where's the charge in the major contributing resonance structure?
On the oxygen.
On the oxygen, on the heteroatom. You're only going to add nucleophiles to alkenes or carbon-carbon pi bonds typically if the resulting anion can be placed on a heteroatom. And that's the case in NAS when you have the rule followed. But also in the Michael. We're able to do this because the anion, again, major resonance structure falls here. If we had a longer chain out here, it would be more of an isolated alkene, and you wouldn't be adding nucleophiles. Okay. A common reaction we'll have to end here. We'll have a quiz on Wednesday. Okay. Since last quiz. Be our last quiz of the semester, most likely. Have a good week, guys. Bidding report, yeah, working group reports. Finishing up strong, yeah?